Thank you for the introduction and good evening, everyone. I am Jubica, and today I will highlight the differences in the performance of pipeline steels in in-stock and excavated conditions in the presence of hydrogen. This project is in collaboration with Labosute, Fluxus, and Ford Economy, and it's also a part of the project that Laura just spoke about. So I will take you through the key sections of my work under the following topics. An extensive pipeline network already exists in Europe. Repurposing or reusing these pipelines for hydrogen service makes sense for a speedy energy transition to achieve carbon neutral goals. This measure is not only cost effective, but economical. However, directly swapping the natural gas with hydrogen gas is challenging because now we all know how hydrogen can impact the material properties of these pipeline steels. In addition, factors such as the age of the pipelines, the in-service degradation due to the natural gas transport, and the manufacturing technology all have significant impact on how hydrogen interacts with these steel materials. Hence, in this context, the focus area of the project is to compare two versions of the L485 pipeline steels and wells in two conditions, that is stock and excavated. For simplicity, for the further part of this presentation, I will abbreviate the stock as A and excavated as B. The difference between them is that the stock material was never used for the natural gas service, whereas the excavated one was used for 30 to 40 years for the natural gas transport. This indicates that the excavated material has already stood the test of time and that it has, including the consequences of the cathodic protection over protection, that also forms an external hydrogen source. So the question exists, can this be still repurposed for hydrogen service? Let's find out. The micrographs here are taken from the pipeline middle region along the rolling direction. Both these materials have a highly banded microstructure throughout the thickness of the pipeline, consisting of ferrite and pearlite. In the middle thickness, we also see the presence of segregation bands, with lots of inclusions present there due to the segregation of elements. The difference between the BMA and BMB is based on the ferrite grain size and the pearlite fraction, both of them being higher for the stock material as compared to the excavated one. The wells are the same material as my colleague Laura just explained. So the material microstructure is very heterogeneous due to multiple weld passes. This is because the microstructure in the vicinity goes through several thermal cycles, and this leads to its heterogeneous microstructure. Prior to all the mechanical tests that was done, it was necessary to know the condition that exactly saturate our base materials before the testing. So we extracted 6 millimeter cubes from the pipeline middle region and then electrochemically charged them at the given current, at the given current density for different charging durations, and then hot extracted them at 900 degrees Celsius to know how much hydrogen we are actually putting into these samples. And we see that, that for all the charging durations, the excavated material show a significantly higher hydrogen uptake at all the conditions. The round bars here are also extracted from the pipeline middle region, having different notch geometries, simulating different stress conditions. Then, based on the conditions that we acquired from the hot extraction exercises, we applied the same conditions and charged our samples electrochemically until saturation, and then subjected these round bars to tensile test at a constant strain rate. From this kind of experiment, we acquire two kinds of information. One is more qualitative, saying the visual impact of hydrogen on these pipeline steels, and then a more quantitative information that is given by the force displacement curves and the hydrogen embrittlement indices. In this presentation, I will only focus on the R6 geometry due to the time limit. As a side note here, we also did the Vickers hardness test at 10 kgf force to know how the hardness is varying throughout the thickness of these samples, of this pipeline material. And we saw that BMA has a higher hardness than that of BMB. This implies that the resistance to plastic deformation of BMA is less than that of BMB. This is also confirmed by the tensile test experiments that was done in the reference condition for the smallest stress triaxiality. And this is shown by the lower elongation of BMA as compared to that of BMB. As expected, the performance of both these materials degraded in the presence of hydrogen, more for BMB, as can be seen in this plot, as compared to BMA. The fracture surfaces also show mostly quasi-cleavage or a brittle kind of fracture for the hydrogen-charged BMB. To put a number to it, the hydrogen embrittlement indices of GWB was 70% in contrast to 13% of BMA. And this is based on the area reduction part of this curve. Since these specimens were electrochemically charged until saturation before the tensile test, so high hydrogen is already present at the center of these samples as compared to the edge. This is because of the fast diffusion of hydrogen through these materials. As expected, when we zoomed into the central region, because that was the most interesting part, we saw that for the reference condition, there was an extensive microvoid coalescence. And even BMB showed traces of the segregation bands. For the hydrogen charged sample, a more characteristic quasi-cleavage kind of fracture was seen. Further look into the desorption data shows that a higher desorption peak is present for BMB as compared to BMA, and this accounts for its high hydrogen uptake. Going deeper into the desorption data, fitting it, and then deconvoluting it to sub-peaks, we see that both of these materials have similar overlapping peaks because of their similar microstructure. Moreover, these peaks are only until 200 degrees Celsius, which is where the reversible traps are present. So we assume that the main players for taking up hydrogen in these materials are grain boundaries and dislocations. If you remember, BMB has a lower ferrite grain size, which indicates that the grain boundary density in BMB is higher than that of BMA. So this can also lead to its high hydrogen uptake. Indeed, more work is needed here to know the activation energies of the traps for hydrogen desorption, to know actually which kind of traps are involved for such a behavior. Similar behavior is also seen for the wells, and that the GWB had a higher degradation than GWA. In the fracture surfaces, apart from the brittle fracture, we also, like quasi-cleavage, we also saw fish eyes in these wells. A quantitative information is that 88% of embrittled GWB in contrast to only 40, okay, not only, but 40% of embrittlement. And this is based on the area reduction. The reference samples showed ductile fracture having both regular and shear dimples along with large intrusions forming part of the ductile fracture. And in the fracture surfaces, along with the coarse cleavage, we have fish eyes. This is also the images that are taken from the central region. Further look into the desorption data, we see that for GWB, multiple peaks are present that obviously account for its high hydrogen absorption than GWA. Looking close to this GWB material, we see that even for the uncharged condition, 2 peaks having almost 7 weight ppm of hydrogen are already present. Comparing this with the charged condition, we are already having an extra peak 1 due to the reversible traps like dislocations and grain boundaries. A deeper look into the peak 3 suggests that retained austenite or its interfaces are contributing to this high uptake. Another fact is that since both peak 2 and peak 3 are similarly present in the charged and the uncharged condition, maybe these traps are not being charged by us, but are already present from the production. Maybe another trap sites like strain cementite ferrite interface that is shown by the peak 2 and peak 3 of the retained austenite interfaces are all contributing to its high hydrogen uptake. So the key takeaways from this study is that both the pipeline steel versions are having a very heterogeneous microstructure. The excavated materials are more prone to hydrogen embrittlement for their high hydrogen uptake, and that for the brittle fracture that they have. Then BMB has a higher trapping density than BMA, and that they have a similar trap types shown by the desorption peak. And then that the presence of retained austenite can contribute to this high hydrogen uptake by GWB. Thank you for your attention.